Alright, today I'll talk about the problem fence loops. So in this problem, we will treat each fence as a node, and then we will basically use an adjacency list to keep track of whatever is on the right end of the left end of this node, and whatever is on the right end of this node. So after we treat this all as node instead of edges, we will be able to use a DFS on this. So here is the code. First, I will receive whatever is on the left of this current fence S. So the first one, I'll just assume that is the left end, and the second input will be the right end. But it works if you change it to the other way around as well. So I'm receiving another fence, and we will push this fence V into the left adjacency list for S, which I created here. I created two. One is to keep track of whatever is on the left end of a fence, and this one will keep track of whatever is on the right end of the fence. So I'll push this into the left end, and I will set this position as V to L. This means that V is on the left end of fence S, and then we're receiving whatever is on the right end of fence S. So also the same, but this time we change it to the right adjacency list, and also we change this letter to R instead. So after we receiving all the input, we will loop through all of the fences that we have. So we'll think of these ones as the starting and ending points, and we will check whether this one has the most optimal of smallest parameter, and so we'll use DFS on this. This DFS function will receiving two parameters. The first part is U, meaning which node we're currently at, and the second one is P. This means which end of the fence we already searched. So I have to keep track of which end we searched, because, for example, if here at this fence we just searched the right end, let's say we just searched the left end of this fence 1, then that means we cannot search through this left end again. We have to go through the other end. Since we came from the left side, we have to go through the right side. And the same thing will happen if it's vice versa. If we start at the right end, then we cannot traverse anything on the right end here already, because we've already went here to the right end. Then we can only visit the left end. So this is why I have to keep track of which end we are searching. Here I'll just first set this to the left side, because at the end we'll always end up, if we're going a whole loop, we'll always end up on the other end. So you can also set this to the right end. We'll always get the same result as well, because we'll just end up at the left end. So first, after I receive the input, I will create this whole visited array to keep track of all the nodes that we've visited. And at first, it will just be all set to false. So first here, this will check if we've completed a cycle. So the cycle will be complete when we have a node that we visited already. Then that means we're going in a cycle, and we can just return 0 for this, because every time here we'll add the length of this current fence. And if it's visited, we don't want to return anything, because we will already add that length of the fence into the current calculations. And so otherwise, we will first set this to visited, and I'll create this optimal count to keep track of the smallest possible parameter for this current node U. And this is the part where we check if we search the right end or the left end. So if we already searched the right end, we will only be able to search through the left end. And so the other case is when P is equal to L. This means that we've already searched the left end of this current fence U, and we will search the right end instead. So here we will get the minimum of this current optimal value, and the DFS of this other fence that it's connected to. And then here we also have to update which end we searched for this V and U. So we have to return where U is compared to V. So if U is on the right side of V, then we'll just return R. If it's on the left side of V, we'll just have L. And so that will tell us which end of V we just searched. So we will use that in the DFS. It will also give us a value, or you can just return 0 if we've already visited that. and then we add the current length of our we'll add the length of our current fence into this DFS, and we'll compare that with our current optimal value. If it's smaller, then we'll set it to this. And this is the same thing for traveling through the right end instead of the left end. You also get the DFS of this. You don't have to change anything here because this value will already be set when we read the input. So it is also the same thing, adding the length of this current fence U into this as well. And then here we can set this visited to false again because we might need to loop through this node again some time later in this recursion. So after that, we will return our optimal value. And so we'll just search every possible fence, and after that we can just get an answer. First I set the answer to the maximum, because then anything smaller than that would just give us a smaller answer. So we'll just compare our current answer with this new value that we just got. If the new value is smaller, then we'll set our answer to that, and we can print out the answer at the end.